Hello everyone, my name is Min-Soo Kang. I'm an assistant professor at the School of Computing at KAIST. I'd like to present our KIR proposal titled Securing and Improving BFT Consensus Protocols with Advanced Networking. Let's start with the main motivations of the project. As we all know, there exist many blockchains that run based on the Nakamoto Consensus Protocol or Proof of Work Protocol, such as Bitcoin or Ethereum or Monero, just to name a few. Another set of blockchains run on BFT or Byzantine Fault Tolerant Consensus Protocols, such as Clayton or Hyperledger Fabric. They have different pros and cons, as you can see in this table. BFT consensus protocols like Clayton mostly form permissioned networks, and one big advantage of them is that they have guaranteed consensus finality. Although it is less scalable, it tends to be less scalable, it is significantly has a better throughput performance and latency performance. As we explained, Clayton runs a BFT consensus, in particular Istanbul BFT consensus protocol. It forms a governance council or GC, which consists of a few tens of highly reputable organizations around the world. As you can see in this mesh network at the center of this figure. And for each block generation, randomly selected group of nodes in the GC, which is called the committee, will be formed, which is really a subset of GC. And the size of the committee for each round is carefully chosen so that it can target a sweet spot that ensures fast and efficient operation of Istanbul BFT protocols. Many of those characteristics of such BFT protocols have been extensively studied. However, it is often neglected that these blockchains actually operate on top of the existing internet infrastructure. So these Clayton nodes in this figure are in fact deployed in different geographic locations, as you can see in this figure, where they have all different locations, and in fact they have their own IP addresses and they are hosted in different networks. And their end-to-end communication sessions are built across multiple internet service providers that are already there. So this really means that if there's any issue with the underlying internet infrastructure, that can potentially affect the security and performance of these blockchains, like Clayton. So that's why the underlying networking layer of blockchains, especially permissionless blockchains, has been the main focus of many recent academic studies. Here, we list a few examples. First, there has been a lot of work, network measurement studies, research, on mostly Bitcoin and Ethereum. So Bitcoin and Ethereum nodes are very well known to have a high node centralization on the cloud providers. And there has been lots of studies, including this one in 2020, that shows that Bitcoin mining power has such severe centralization. Second, peer-to-peer network topology of the Bitcoin and Ethereum has been really extensively studied. And several work like Miller et al. And Delgado et al. In 2015 and 19 shows that it is possible to learn the P2P network topology of Bitcoin. And learning Bitcoin P2P topology is actually quite serious, a serious issue, because it can actually lead to transaction traceability of Bitcoin, which is actually a big problem in transaction privacy. So there has been some countermeasures that makes Bitcoin transactions less traceable by making those P2P topology a little bit more complicated than before. And third, there has been several attacks that shows that Bitcoin's P2P network can be easily partitioned. So the very recent work proposed by our own group shows that Bitcoin network can be partitioned very easily, unfortunately. And there are some other works that shows that Bitcoin network can be eclipsed and even some of the connections can be easily hijacked. So this recent research trend vividly really shows that the networking layer of blockchains plays a significant role in particularly in permissionless blockchains like Bitcoin and Ethereum. Then the natural question is, what about the networking layer of permissioned blockchains like Clayton's and many other BFT-based blockchains? That's exactly what we're going to explore in this KIR project proposal. So we believe that having a better understanding of the underlying network infrastructure for BFT-based permissioned blockchains is crucial for their secure and successful operations. We make two important observations. One is about security of BFT blockchains. Two is about the performance of BFT blockchains. Let me explain these two observations in this following slides. So first, we observe that the underlying network infrastructure may constitute a serious threat to the reliable blockchain operations, especially BFT blockchains. If you look at the classical BFT studies, they basically all, in the literature, they all assume that their nodes are well distributed in many different geographical locations. And when the nodes are highly distributed and they have good connectivity diversity, their connectivity, end-to-end connectivity, is pretty diverse, which means that it would be hard to find any sort of choke points or common intersections of those connections in their peer connectivity. So this diversity can ensure highly reliable blockchain operations in general. However, from previous work, especially on Bitcoin, we learn that that's really hardly the case. Because of the ease of maintenance and cost effectiveness, many of the nodes, existing blockchain nodes, especially Bitcoin and Ethereum, are hosted at large cloud providers. Worse yet, the number of those large cloud providers are not many. So there's a high centralization. And those high centralization is really the reason that enables several particular network attacks in Bitcoin and Ethereum. So what we are worried about is that the node distribution of permission blockchains like Clayton or many other BFT blockchains can be also low as well. But this has never been thoroughly studied before, so that's really the problem. So we don't really know how well the nodes are distributed in existing permissioned blockchain networks. That worries me. What worries us more is that the permissioned blockchains tend to have smaller network sizes, which means that smaller network sizes with the centralization of the node, that will cause a more problem than we had in the permissionless networks. So one very important but unanswered question is, how are the existing BFT protocols robust or vulnerable to attacks launched by malicious network operators like malicious ISPs or malicious cloud providers? So we don't have any answers to that yet. There's another observation, that is, in-network programmability has a great potential in improving the scalability of consensus protocols. So very recently there are several work that show that classical consensus protocols like Paxos can be greatly simplified by dividing its consensus responsibility to the network switches. So one notable work is this No Paxos work by Lee et al. In 2016, which shows that they can build a replicated system based on Paxos with only 2% of latency overhead compared to this unreplicated system. Unreplicated system meaning just single system. And with only 2% latency overhead, they can achieve replicated systems based on Paxos. So this is a very surprising result compared to the traditional Paxos. And this surprising result really comes from the fact that some simple tasks, like consensus-related tasks of those protocols like Paxos, can be offloaded to the switches, network switches, and those tasks can be very simple, like message ordering. And when that happens, the Paxos protocol can be significantly simplified. This idea has become more practical than ever with the emerging programmable switches that ensures line rate operation of messages with terabit per second capacity. So for example, Intel's Tofino Ethernet switch can support up to 10 terabit per second, or even higher actually with the newer model. And you can think of it as a more general version of SDN, and in the sense that you can write some, not arbitrarily, but quite useful code for the switches for the line rate operations. So one important, but again still unanswered question is that, can Istanbul BFT protocols be simplified with the help of these programmable switches by offloading some of the consensus mechanisms to those switches, just like Paxos has been so simplified with those programmable switches? Can we do that or not? We don't have any answers to that yet. Let us now take a look at the research tasks in this KIR proposal. In the first task, we are going to do some network attack analysis on Istanbul BFT. So basically, we're going to analyze potential risks of Istanbul BFT consensus protocols against network adversaries like malicious ISPs or malicious cloud providers. So here are the research items. We first will conduct a measurement study on an existing blockchain network like Clayton, and we're going to evaluate potential network attack scenarios for Clayton and list potential threat actors. And then we're going to suggest a routing-aware node placement for Istanbul BFT consensus protocol, which can be readily used for the Clayton operation. And then we're going to suggest a more long-term solution, which can ensure better reliability for the Istanbul BFT consensus protocols, such as like relay architectures. And then we're gonna, in task 2, we're gonna explore the research opportunity for scalable Clayton with in-network offloading. So we're gonna try to scale up the Istanbul BFT consensus protocol with programmable switches. So here are some research items. First, we're gonna prototype line rate Istanbul BFT message processing in programmable switches. And then we're going to analyze the scalability bottleneck of Clayton's protocol. And then we're going to study the potential of offloading mechanisms to switch fabrics for inline computation of the BFT protocols. And we aim to propose an improvement to Istanbul BFT consensus protocol with programmable switches. So this may have different, different stages of the deployment scenarios, like centralized deployment scenario and the distributed deployment scenarios. And we want to achieve higher scalability for Clayton. Let us introduce our research team. So the main PI is myself, Min-Suk Kang, and I'm leading the network security and privacy lab at Kaist. And I'm an assistant professor at Kaist since last year. And before I joined Kaist, I was an assistant professor at National University of Singapore in 2016 to 2020. And I got a PhD degree on network security at from Carnegie Mellon University. Before that, I was trained and educated at Kaist as well. So I'm working on a wide, areas and different subtopics of network security and privacy, including internet security and blockchain security and 5G IoT wireless networks. And particularly, I am very interested in this blockchain security, just to give you an idea of what kind of project I've been working on in this domain, I've been working um, on a scalable Bitcoin mixer that provides a higher transaction privacies, and we built the entire Bitcoin mixer system with the Intel SGX architecture in 2018. In 2020, as I briefly mentioned, we actually presented a novel Bitcoin partitioning attack, which was called the Erebus attack, which is highly stealthier than any other partitioning attacks before this attack. And we actually proposed a couple of security patches to the Bitcoin core team. So our solutions, actually two of our solutions are already deployed in the current Bitcoin core development. And more recently, we actually propose a more fundamental solutions to many of the networking attacks against Bitcoin, which is called routing aware peering mechanism, which hopefully will be included in the next Bitcoin version soon. And I'm leading this network security and privacy research lab at Kaist, and we have three master students, one from School of Computing, two from Graduate School of Information Security, both at Kaist. And we have three highly motivating undergrad interns, all from School of Computing. And I'm also currently still advising two PhD students, both are National University of Singapore, and I'm also advising one undergrad interns at National University of Singapore. So our group, virtual group at Kaist, has quite international environment, and we are working with highly motivated students. And lastly, let us discuss the schedules and deliverables and budgets. Schedule, we plan to complete the entire two tasks within 12-month windows. And we're gonna run this task 1 and 2 in a parallel way. We're gonna start with the task 1, and then by the way, every 2 months we're gonna have this major milestones, milestone 1 through milestone 6. And during this 2-month first period, we're gonna work on task 1 mainly, and then after that, by using the result of the task 1, we're gonna start with task 2. So for the milestone 2 to 3 to 4, we're gonna run task 1 and 2 in parallel, and by the end of milestone 4, we plan to conclude the research work on task 1, and then by the end of milestone 6, which is the end of the entire project schedule, we plan to finish this task 2. So that's the schedule, and there are 3 deliverables, and the first one is technical reports, which is the summary of measurement studies, threat analysis, prototype designs, and countermeasures, and proposed protocol designs. And we plan to have a number of evaluations tools at the end of this project. So we want to share our tools for network measurement studies, network simulations, and code for the programmable switches, and especially we're gonna have an evaluation framework for the Istanbul BFT simulations with inline in-network offloading capability. And if there are any other experimental results that might be of interest to the Clayton community, would be useful for the Clayton community, we're happy to share with all these experimental results. Here's the budget breakdown. A large chunk of budget goes to the manpower, and some goes to cloud services. We do need lots of cloud services for large-scale measurements. Network measurement are basically distributed across the entire world, and we plan to purchase a number of these emerging programmable switches that are quite slightly expensive, more than typical enterprise grade switches, and also we plan to purchase these high performance servers as well. So to conclude, the key takeaways is that the networking layer of blockchains is really highly crucial for security and performance of blockchains. And we want to do this task one, that is to analyze potential risks of Istanbul BFT protocol against network adversaries. And task two, we want to explore how to scale up the Istanbul BFT consensus protocol with programmable switches. So we envision that the result of this project will make Clayton more secure and scalable in the near future. So thanks everyone. Please let us know if you have any questions regarding this KIR proposal. Thanks.